If you've ever wondered why some of the most legendary American cars seem almost indestructible, or why certain engineering mistakes from the past became infamous cautionary tales, you're about to find out. Because today, we're pulling back the curtain on a world most drivers never got to see, a time when engineers couldn't rely on powerful computers, digital simulations, or software that could predict problems before a single part was built. If they wanted answers, there was only one way to get them. They had to build the machine, push it to its limits, and see what survived. Long before computer-aided design, virtual crash simulations, or advanced aerodynamic modeling, automotive development was a hands-on battle between engineering theory and physical reality. Drawings and calculations could only take you so far. Eventually, someone had to turn a key, put a car on a test track, and discover whether the design actually worked. Sometimes it did. Sometimes it failed spectacularly. Today, we're stepping back into the 1960s, one of the most intense and fascinating periods in American automotive history. This was an era when engineers learned lessons through broken components, destroyed prototypes, and endless hours spent testing machines in conditions far harsher than anything an ordinary customer would ever experience. If you want to understand how iconic engines became legends, or why some vehicles developed reputations for problems that still get discussed decades later, you have to understand how they were tested. The story really begins at the proving grounds. Back in 1924, General Motors opened what would become the first dedicated automotive proving ground in the industry at Milford, Michigan. At the time, it covered a relatively modest 1,125 acres and contained only a few miles of testing roads. But GM leadership understood something important. Public roads simply weren't suitable for serious development work anymore. Engineers couldn't safely push vehicles to their absolute limits while sharing the road with everyday drivers. They needed a controlled environment where failure wasn't just accepted, it was expected. Over the following decades, Milford expanded dramatically. By the mid-1950s, the facility contained more than 50 miles of specialized roads designed for testing. Then, in 1964, one of its most famous features was completed, a massive 4.5-mile circular track that would become notorious among engineers. This wasn't a leisurely oval built for comfort, it was a high-speed torture chamber. Cars would run around that track for hours at a time, sometimes days, occasionally even weeks. The objective was simple: accumulate enormous mileage as quickly as possible. Engineers wanted to compress years of ownership into a matter of days and discover weaknesses before customers did. What's remarkable is how primitive the data collection seems by modern standards. There were no laptops connected to vehicles, no wireless telemetry streams, no sophisticated sensors feeding information into massive databases. Most of the equipment consisted of mechanical gauges, recording devices that scratched information onto paper, and handwritten notes. When something began to go wrong, the first warning often came from the driver. Maybe the steering felt different. Maybe a vibration appeared. Maybe an unusual noise emerged. An engineer sitting alongside would record observations manually. That was often the testing process. GM wasn't alone. Ford had its proving grounds at Romeo, Michigan, while Chrysler operated facilities at Chelsea. These locations featured much more than simple speed tracks. Engineers built specialized roads designed specifically to punish vehicles. There were stretches made from rough Belgian block paving that relentlessly hammered suspensions. Washboard surfaces created endless vibrations. Mud pits challenged traction systems. Steep grades tested powertrains under heavy load. Every section existed for a reason. The proving grounds served as the ultimate judge. Mathematics and theory could suggest a design would survive. The test track determined whether it actually would. Engine testing was equally relentless. During the 1960s, General Motors documented many of its engine durability procedures, and the details revealed just how brutal the validation process really was. Before an engine earned approval for production, it had to survive a 200-hour durability test on a dynamometer. At first glance, 200 hours may not sound extraordinary. Then, you look at what happened during those hours. The engine continuously cycled between peak torque speed and peak horsepower speed. Every few minutes, the operating conditions changed. After several cycles, the throttle would suddenly close. The engine would drop to idle. Then, within seconds, it would accelerate back to maximum operating speed and begin the process all over again, hour after hour. day after day, for 200 hours. Every 25 hours, technicians stopped the test long enough to inspect important measurements. Compression checks were performed. Blow-by levels were measured. Ignition timing was verified. Belt tension was examined. Then everything went right back on the dyno. Unlike modern engines, there were no sophisticated control systems constantly adjusting parameters to protect components. There was no electronic brain reducing timing when conditions became dangerous. Carbureted engines simply operated under whatever punishment engineers subjected them to. If a connecting rod bearing couldn't survive, it failed. If a piston developed a weakness, it failed. If a valvetrain component wasn't strong enough, it failed. Then, engineers tore the engine apart, examined every damaged piece, determined what happened, redesigned the problem area, and started again. At GM's Tonawanda engine facility in New York, employees remembered hearing test engines running almost continuously. The sound of engines under load became part of everyday life. This was how fatigue testing happened before advanced computer modeling existed. Engineers physically recreated the punishment and watched what broke. The result of these efforts was a generation of engines that remain legendary today. Power plants like the 396 Chevrolet, Ford's 427, Chrysler's 440 and 426 Hemi, and Oldsmobile's massive 455 became icons partly because they survived testing that was every bit as demanding as their reputations suggest. The next chapter of this story is far more serious because it deals with crash testing and safety research. It also reveals just how little the industry understood about protecting occupants during collisions. In 1934, General Motors conducted what is widely recognized as one of the earliest automotive crash tests when an unoccupied vehicle was sent into a concrete barrier at Milford. The vehicle itself provided useful information. There was an obvious limitation. The work was disturbing, but it produced critical information that simply couldn't be obtained any other way at the time. Researchers also used pigs because their internal anatomy shared important similarities with humans. This allowed scientists to better understand injuries occurring during automobile crashes. One particularly deadly problem involved steering columns. During severe frontal impacts, rigid steering columns often acted like spears. Occupants could be impaled or suffer catastrophic injuries when thrown forward. The statistics were staggering. By the mid-1960s, steering wheel-related impacts had contributed to an enormous number of fatalities. To address this problem, engineers developed the collapsible steering column. Rather than remaining rigid during a collision, the column could compress and absorb energy. The improvement was revolutionary. Physical crash testing demonstrated that this single innovation dramatically reduced the risk of fatal steering wheel injuries. Milford continued advancing crash research, constructing more sophisticated barriers, and improving testing procedures throughout the decade. Then, in 1966, public attention toward automotive safety changed dramatically when Ralph Nader published Unsafe at Any Speed. The book became a national bestseller and placed unprecedented pressure on lawmakers. Congress responded by passing the National Traffic and Motor Vehicle Safety Act that same year, laying the groundwork for modern safety regulation. The National Highway Traffic Safety Administration eventually followed in 1970. One key figure was Maurice Alley, a brilliant engineer whose contributions fundamentally changed vehicle dynamics development. He believed ride quality and handling should be evaluated through careful observation of how people actually experienced a vehicle. Many of the exceptionally smooth American cars of the era owe their ride quality to this process. The floating sensation associated with large GM sedans wasn't accidental. It resulted from years of systematic development and evaluation. Of course, human feedback introduced challenges. Engineers solved this problem by creating a shared technical language. Terms like jounce, float, wallow, and thud weren't casual descriptions. Each represented a specific handling characteristic understood throughout the engineering community. No matter how sophisticated the software becomes, eventually every design must prove itself in the real world. As one longtime GM testing executive once explained, mathematics can predict how a component should perform, but true confidence only comes after real drivers use real vehicles under real conditions, again and again, until the answers become undeniable. That philosophy built some of the most memorable cars ever created, and in many ways, it still guides automotive engineering today.